Alright, let's move on to trees. I haven't done this section of the worksheet, but we can probably just work through it together. Hopefully I don't mess up. Yeah, looks like there's 2 or 3 problems in there. So let's do the first one. So it says the total weight of a tree is defined as the sum of the labels of all of its nodes. A tree is defined to be equally weighted if the total weight of each of its branches is equal. A leaf is assumed to be equally weighted. Alright. So they have given us a total weight function here, and we have to implement the equally weighted one. So I guess we should probably draw some sort of tree. Let's say my root is 1, I have a 2, a 3, and a 4. Alright, and looks like this would be an example of an equally weighted tree, because each of the branches is equally weighted, they both have 4. Alright. So they're doing some sort of list comprehension, and then a for loop. Okay. So I'm thinking the list could be either a list of Boolean values or maybe a list of like the weights of each of the branches. So let's say in this case it was the weights of each of the branches. So if the list was 4, 4, 4, we'd want to return true. But I can't think of a way to iterate through this for loop and sort of do the like check if they're all the same number. We could potentially also have Boolean values, but I don't think that's the right approach because we don't want to be calling equally weighted on each of its branches, because the only condition we have to satisfy is if the total weight of each of its branches is equal. Okay. So by default, I'm guessing we return true. And here this could probably be our false condition, so if something is violated. Okay, so I guess let's start with the original idea I had of having these weights and then having the total weight of each branch in this list. Okay. I guess we could do like use indexes. So this would be index 0, index 1, index 2. And then at each index, I'd compare something to its neighbor. That could work. So let's say for I in range 0, so that's just implicit, but I guess we'll leave it, comma len of weights. And then we want to compare weights of I to weights of I plus 1. So if weights of I is not equal to weights of I plus 1, then we have a discrepancy. That means that not all of the weights are the same, and so then we'd return false. There's a slight problem with this, because once I'm at the last index, so once I'm at index 2 in this case, then I'd be trying to compare to index 3, and that would be out of bounds. Luckily, I already have compared 1 to 2, so I just do 0, comma len weights minus 1. So the reason this works is because you have some starting element whose value is 4, and then you compare that element to the next one. If they're equal, then you're good, and you move on to the next one. That means the first 2 elements are equal, right? Then once you get to the second element, you compare it to the third one. And that means the second and third elements are equal. And that essentially ensures that the entire list has to be equal. Alright, I think this works. Let's make sure we're on the right track. Okay, so they did something slightly different. They do have all weights as all of the total weights, but they just compare each weight to weight on like the front weight. Okay, so what this would be doing is you'd have like 4, 4, 9, perhaps. Let's make this bigger. 4, 4, 4, 9. And then you'd be comparing this 4 to this element, then this element, and this element. Okay, yeah, that seems perfectly reasonable as well. But yeah, what we did looks okay as well. Cool. Let's do the next one. So this says, return the number of equally weighted subtrees of T. Okay, and note that T is considered a subtree of itself. Okay, let's see if there's any more description about this problem. Okay, there isn't. So I'm not fully sure what they mean here. Do they mean immediate subtrees? Or I'm guessing they don't mean immediate subtrees. But let's draw out like the doc test. So we have 1, 4, 3, and 3 has a child of 1. So the answer to this, so this subtree is weighted 4, this subtree is weighted 4, and T itself is weighted like 9, right? And then, I'm wondering how they got 4 here. Maybe I'm misunderstanding some part of the problem. Return the number of equally weighted subtrees of T. Note that T is considered a subtree of itself. Oh, okay, right. So equally weighted was defined as a tree in which the total weight of each of its branches are equal. So the question here is, okay, is the tree 1 with root at 1 equally weighted? And it is, because both of its branches have the sum 4. Okay, so that's one tree. Let's color it blue. Is this node equally weighted? Yes, it's just a leaf. Is the 3 tree equally weighted? Yes, because it only has one branch, and it has the same weight as all of the other branches. And then this 1 tree is also equally weighted. Okay, yeah, sorry about that. I guess I was misunderstanding something. Okay, so let's take a quick look at the template. So they have some value, val, and then it's computed somehow. If something, you return, and then otherwise you just return val. Okay. So I think the distinction here we might be making is that in one case you might include your own tree, and in the other case you would not. So like maybe in this case you return val plus 1 if your own tree is equally weighted. That's just a guess. But that would mean that val is the number of equally weighted subtrees in your own tree. So we somehow want to call num EQ weighted on each of the branches. Okay, so let's do that. So maybe we make a list that stores the result of calling num EQ weighted on B for B in T dot branches. Okay. And what that means is we would get if we're at the root, so if we're at the 1 node, then we'd get a list that has 1, 2. The reason why is because there's 1 equally weighted tree on the left side and 2 equally weighted subtrees on the right side. Okay. And then we want 3 from that, right? So we want the sum of that. Then, if your tree itself is equally weighted, so if equally weighted on t is true, then you just return val plus 1. Yeah, that seems reasonable to me. Maybe we'll try it on one other doc test that doesn't have all of its subtrees equally weighted. So we have 1, a tree with 9, a tree with 1 who has children 4, and 3 who has a child 1. Okay, so the total weight of this tree looks like 10, 14, 17, 18. Oh, I'm not sure why I'm doing the total weight. So the total weight of the left tree is 9, and the total weight of the right tree is also 9. So our root node is equally weighted. This is a leaf, equally weighted. This is a leaf, equally weighted. This is a leaf, equally weighted. This 3 node is equally weighted. And is this 1 node equally weighted? It has a 4 on the left side and a 4 on the right side. Okay, well that's not good. I guess everything is equally weighted. But, oh well, that's okay. Let's run our algorithm on this. So what our code would do is it would say val is equal to the sum of this list that we come up with here. So there's only 2 branches. So the number of equally weighted trees on the left side, that's just 1. And on the right side, that's 1, 2, 3, 4. That's 4. Okay, so that would be, val would be the sum of this, which is 5. Then we'll call equally weighted on t. So if this 1 is equally weighted, it is. So we'd return 6. All right. Yeah, that seems to work. If you guys are wondering about any base case we might have, well, let's say we were at this leaf node. We'd get the sum of an empty list because the leaf node has no branches. So that would just be 0. And then if that tree is equally weighted, it is. We said a leaf is equally weighted as per the previous function. Then we'd return 0 plus 1, which is 1. So that looks good to me as well. Let's just make sure. Okay, looks good. Alright, so this next one looks like it's about rotating trees. So implement rotate, which takes in a tree and rotates the label at each level of the tree by 1 to the left destructively. Great. This rotation should be modular. That is, the leftmost label at a level will become the rightmost label after running rotate. Okay, and you do not need to rotate across different branches. I'm not sure exactly what they mean by don't rotate it across different branches, but that's okay. Let's look at the example. For example, given the tree t on the left, rotate of t should mutate t to give us the right tree. So let's just draw this. 1, 2, 3, 5. Okay. And what we would do is rotate to the left. So this 3 would become our leftmost node, then the 5, and then the 2. Right? That's what they've done. And what they did was they made the 4 a child of the 5. Okay. So what that means, okay, so the branches don't get rotated. So a 4 was in the middle, it remains in the middle. Good to know. Alright, so we have this method description, rotate of t. There's some variable branch labels. We get the length of the branches, so we probably iterate through. So let's temporarily put this for I in range n. And branch labels is probably storing the labels of each of the branches. That seems reasonable. So we'll have an array, use a list, using a list comprehension, where we'll get b.label for each of the branches. So for b in t dot branches. Okay, and what this contains is this list 2, 3, 5, right? Okay, so what we want to do is we essentially want to change the labels of each of the trees. Because if we only change the labels, so if I simply just made this a 3 and then made this a 5 and then made this 3, then I don't need to mess with the children of anything. So I'm looping through for I in range n. So if I'm at, say, I equals 2, then, so that would mean this one right here. I want its value. Let's do a one in the middle. Let's say I was at I equals 1. Then I want the value there to be the value that was originally at I equals 2, right? So I want t dot branches at I dot label to be t dot branches of I plus 1 dot label, right? Except that that messes up at the edge cases, but let's see what that does for us. So let me write this. T dot branches of I dot label is equal to t dot branches at I plus 1 dot label. Okay, so the way I can deal with the last case is, well, I say that when I'm at I equals 2, then I actually want I equals 0, right? So for I equals 2, I'll say, give me the thing at, I get my regular 2 plus 1, which is 3. How do I convert that 3 to a 0? I can take the mod. So 3 mod 3 would give me 0. So what that means is that whenever I overflow to the right by 1, then that just resets me back to the front. So let's just look at the examples. So at I equals 0, which would be here, get I equals 1, because that's the one to its right, so that'll become a 5. Then at I equals 1, we get I equals 2, so that becomes a 2. And then at I equals 2, I get 3, but 3 just becomes a 0, so that gets me 0. Okay, and I don't want to use t.branches, because I'm changing t.branches as I go. So that's not going to work out for me. For example, I will have changed this first one to a 5, but then I'll try to set it to a 3 here later, and that won't work. That's why we made this like branch labels. So we'll use branch labels, and then instead of doing I plus 1, we'll just do I plus 1 mod the length of t.branches. Oh, we have n. Cool. And then I don't need to do dot label because I'm already storing the labels. This is already a list of numbers. Alright, I'm not sure what the other two lines are for. I believe this should work. Let me take a look. Oh, I guess I missed something. Okay. So branch.label is equal to branch labels of I plus 1 mod n. Okay, that part is fine. But then they actually called rotate on branch. Okay, so I guess this was a misunderstanding of the problem. Yeah, we didn't have a test case where there was this branch and then there were, say, multiple things in here, like a 3. But I probably should have thought of that. Let's see. Rotate takes in a tree and rotates the label at each level of the tree. Labels. Okay. Yeah, so that was my bad. So we'll just call rotate on t dot branches sub I. All right. Yeah, that should be good. I'll be back with generators.